August 20th, 1942, 10:47 p.m. Henderson Field, Guadalcanal. A massive explosion tears through the darkness, then another, and another. Japanese destroyers offshore are hurling 5-inch shells directly at the airstrip, where just hours earlier, American fighter planes landed for the first time. The coral runway is cratering under the bombardment. Supply dumps are erupting in flames. Men are diving into foxholes. But here's what doesn't make sense. In the middle of this hell, with shells screaming overhead every 30 seconds, a group of Navy Seabees are still working. They're operating bulldozers, laying steel planking, filling bomb craters with crushed coral. One man is measuring runway gradients with a surveyor's level while shrapnel pings off nearby equipment. These men aren't heroes frozen by duty. They're engineers solving an impossible equation. How do you build a functional military airfield when the enemy is actively trying to destroy it? How do you grade a runway to within 3-degree specifications when artillery shells are creating new craters faster than you can fill the old ones? This is the story of military construction's most extreme challenge, where bulldozer operators became combat veterans, where concrete mixers doubled as fighting positions, where the difference between a properly graded runway and defeat could be measured in a single degree of slope. But what they didn't know on that August night was that their techniques would revolutionize military engineering forever.
Let me take you back to July 1942. The Pacific War had been raging for 7 months, and the Japanese military had just made a critical decision that would change everything. On the island of Guadalcanal in the Solomon Islands, Japanese engineers surveyed a flat stretch of ground at Lunga Point. Perfect. They brought in 2 massive construction units, 1,379 men in one group and 1,145 in another. These weren't just laborers. They'd originally been designated to build facilities on Midway Island after Japan captured it. But Midway never fell, so they were redirected here. They arrived on July 6, 1942, and began work 3 days later. Their mission? Construct a bomber base that would cut the supply lines between the United States and Australia. From this airfield, Japanese aircraft could patrol the southern Solomons, threaten shipping lanes, and establish complete air superiority over the region. The construction moved fast. Too fast. Allied coast watchers hiding in the jungle hills watched through binoculars as the dirt runway took shape. They radioed the coordinates to Allied command. By early August, the runway was nearly complete. On the night of August 6th, the Japanese construction troops received an extra sake ration. They'd finished ahead of schedule. They celebrated for one night. The next morning, August 7th at dawn, the U.S. 1st Marine Division hit the beaches. The Marines overwhelmed the surprise defenders and captured the airfield virtually intact. It was 3,800 feet long and 150 feet wide, made of packed earth, poorly drained, and absolutely critical to whoever controlled it. The Americans immediately renamed it Henderson Field, after Major Lofton Henderson, a Marine aviator killed at Midway. But here's where the real problem began.
The Japanese wanted Henderson Field back, desperately, and they were going to pound it into oblivion until they got it. On August 20th, the 6th Naval Construction Battalion Commander, Commander Joseph P. Blunden, reported to General Vandegrift with his unit of approximately 400 Seabees. His orders were simple on paper: maintain and expand Henderson Field. In reality, he was being asked to build and maintain a functional combat airbase while it was under constant attack. Think about what that means practically. A combat aircraft like the F-4F Wildcat fighter needed a runway with specific engineering standards: maximum grade of 3 degrees, surface compaction to support 8,000-pound landing gear loads, drainage systems to prevent flooding, width of at least 150 feet for safe operations. Miss any of those specifications by even a small margin, and planes crash on landing. Wheels sink into soft spots. Propellers strike uneven surfaces. Pilots die. Now try to achieve those specifications while Japanese destroyers offshore fire 752 8-inch shells at you in a single night, while bombers drop 500-pound explosives, while enemy artillery zeroes in on your grading equipment. The Seabees developed a technique that sounds insane but worked brilliantly. They worked in rotating shifts around the clock, never stopping. When bombardment began, some men would operate equipment, while others manned defensive positions. Bulldozer operators learned to work with their heads below the protective steel blade, using it as armor. They positioned fuel dumps and supply depots in dispersed locations so one hit wouldn't destroy everything. But the biggest breakthrough came when they discovered the Japanese bombardment pattern. The enemy ships would shell the same sections repeatedly, the ones they knew contained aircraft parking areas and fuel storage. So the Seabees did something clever. They kept those areas maintained, but moved actual operations to different sections each night. They built decoy fuel dumps. They parked wrecked aircraft in targeted zones as misdirection. Meanwhile, they focused their construction effort on runway repair and extension. They discovered that the original Japanese runway base was too soft for heavy American bombers. The solution? A material called Marston mat.
Marston mat, officially called pierced steel planking, or PSP, became the secret weapon of Pacific airfield construction. Each plank was 10 feet long, 15 inches wide, and weighed exactly 66 pounds. Made of manganese steel, it was perforated with 87 holes to reduce weight and allow drainage while maintaining structural strength. Here's the genius of the design. The planks interlocked with hook and eye connections. 3 or 4 men could link them together quickly, creating a continuous metal runway surface. The perforations allowed grass to grow through, camouflaging the runway from aerial reconnaissance. The steel could support a fully loaded B-17 bomber weighing 65,000 pounds. The average laying speed? 125 square feet per man-hour. That meant a 4-man crew could lay 500 square feet per hour. A complete 5,000-foot runway required approximately 450,000 square feet of matting. Do the math. With sufficient crews working continuously, you could lay a bomber-capable runway in about 10 days. But here's what made it revolutionary under combat conditions. When a shell crater appeared in a steel-planked runway, repairs were simple. You didn't need concrete to cure or coral to compact. You filled the crater with any available material, rough-leveled it, and laid new planking over the top. A crater that would take days to properly repair with traditional methods could be flight-ready in hours with PSP. On Henderson Field, the Seabees laid over 6,000 individual Marston mat sections under constant bombardment between August and November 1942. They developed techniques to work at night without lights, positioning planks by feel and sound. They learned to identify incoming shell caliber by the whistle and adjust their workflow accordingly. When Japanese battleships Kongo and Haruna fired 918 14-inch shells at Henderson Field on the night of October 13–14, 1942, the devastation was catastrophic. Fuel dumps exploded, aircraft were destroyed, but by 2 p.m. the next day, the Seabees had the runway operational again. Damaged planes that had been circling desperately were able to land. However, the biggest challenge was still ahead.
Let's talk about what it actually meant to be a construction engineer in these conditions. Between August and November 1942, Henderson Field was bombarded 23 separate times by Japanese naval forces.
Artillery fire was nearly continuous when enemy ground forces pushed close. Air raids occurred almost daily. Every single construction mission happened under threat of death. The 6th Naval Construction Battalion suffered casualties that shocked military planners. These weren't combat infantry. They were carpenters, surveyors, equipment operators, and concrete specialists. Yet they worked in conditions more dangerous than many frontline units. The worst period came during the Battle for Henderson Field in October 1942. Japanese forces launched coordinated land, sea, and air attacks attempting to overrun the position. For 3 days, the Seabees alternated between operating construction equipment and manning defensive perimeters with rifles and machine guns. They loaded aircraft with bombs while under artillery fire. They repaired runway craters while enemy snipers targeted them from the jungle tree line. One Seabee operator named in the 6th Battalion's cruise book described working his bulldozer during a bombardment. He kept the blade raised to protect the cab and worked blind, with a spotter lying prone nearby shouting directions over the engine noise. When a shell landed 50 yards away, he didn't stop. "If I stopped every time something exploded, the runway would never get finished," he said. This pattern repeated across the Pacific. At Iwo Jima in 1945, the 133rd Naval Construction Battalion suffered 370 casualties out of 875 men during the 26-day battle. That's a 42.3% casualty rate. They had 2 missions: clear mines and repair the airfield while Marines fought to capture it. The Navy Seabees suffered some of the highest casualty rates of any non-infantry unit in the entire war. But what they learned in these hell conditions changed military engineering forever.
From the crucible of construction under fire, aviation engineer battalions and naval construction battalions developed techniques still used today. First, equipment redundancy and dispersion. Instead of one large equipment pool, they maintained multiple small caches hidden in different locations. Lose one bulldozer to shelling, and you add backups. Second, modular construction techniques. Everything was designed to be assembled quickly from prefabricated components, not just the Marston mat runways, but also fuel systems, lighting arrays, and drainage infrastructure. Bomb a section, and you could swap in replacement modules within hours. Third, continuous operation protocols. Traditional construction has phases: survey, then clear, then grade, then surface, then finish. Under combat conditions, all phases happened simultaneously. One crew surveyed while another cleared, while a third laid matting. When bombardment hit, crews rotated into defensive positions, then immediately resumed work. Fourth, the Aviation Engineer Battalion Standard emerged. 850 men lavished with equipment. Diesel tractors, bulldozers, carry-all scrapers, graders, gasoline-powered shovels, rollers, concrete mixers, air compressors, pneumatic drills. A self-contained construction force capable of building a combat-ready airfield from raw jungle in 5 to 10 days. That's not marketing. That's the actual documented timeline achieved repeatedly in the Pacific Theater after 1943.
Today, if you fly into Honiara International Airport in the Solomon Islands, you're landing on Henderson Field. The runway has been expanded and modernized, but it's the same location where Seabees worked under bombardment in 1942. The techniques developed under fire became the foundation for modern military rapid runway repair. The U.S. Air Force's Red Horse squadrons, the Navy's NMCB units, the Army's engineer brigades all trace their doctrine back to lessons learned at Henderson Field, Iwo Jima, and dozens of Pacific airstrips built while being shelled. Think about that. Every time you see military engineers deploying to establish a forward operating base, they're using techniques refined by men working bulldozers under artillery fire. The modular construction approach, the equipment dispersion doctrine, the continuous operation protocols, all of it was developed in the most extreme construction environment imaginable.
The 6th Naval Construction Battalion's motto became "We build, we fight." It wasn't just a slogan. It was their daily reality for 4 months on Guadalcanal. So the next time someone tells you construction work isn't dangerous or impressive, remember Henderson Field. Remember men measuring runway grades while shells exploded nearby. Remember engineers who became casualties at rates comparable to infantry. Remember that the airfield keeping fighters operational might have been repaired hours earlier by someone operating a bulldozer with a rifle slung across their back. They didn't just build under fire. They revolutionized military engineering while doing it.
If this story of engineering under extreme conditions fascinated you, this channel has dozens more. From the radio networks that coordinated D-Day to the bridge-building techniques that crossed the Rhine in 1945, we explore how military engineers solved impossible problems. Hit subscribe and tap the bell so you don't miss the next video. We're diving into the secret communications systems inside POW camps next week. Trust me, you won't believe how prisoners engineered entire underground networks right under their captors' noses. Drop a comment below. What other military engineering challenge should we cover? What problem-solving story from history do you want explained? Thanks for watching, and remember, sometimes the most impressive victories happen not with weapons, but with bulldozers and brilliant engineering.